All right, so the pH in our blood is about 7.4. The range is known to be between 7.35 and 7.45. It actually can deviate as low as 7.0 and as high as 7.8. However, it cannot really deviate much further than that and be a survivable condition because of the reasons we stipulated in the previous video. So why is it that we have this wide variety of ranges in pH? Why is it that it fluxes back and forth from sometimes disparate numbers? Usually the pH fluxes are a byproduct of physiological processes. So, on a regular basis, your body is outputting usually acidic substances, phosphoric acid from the breakdown of phosphate containing nucleic acids. Of course, lactic acid, which is produced from glycolysis, which is probably the best known of the byproducts, the acidic byproducts. When we metabolize our fat, we produce fatty acids and ketone bodies, both of which are acidic. And then we have, of course, one basic substance, which is the bicarbonate ion, which comes from the loading and transport of carbon dioxide. We talked about the breakdown of carbon dioxide in the presence of water, along with the substance carbonic anhydrase to create carbonic acid, and then that's broken apart into hydrogen ions and the bicarbonate ion. We talked about that with the respiratory system. So these kind of things must be dealt with. These kinds of substances that are put out by your body on a regular basis must be balanced correctly. And there's three ways that we control our pH balance. The first of them I'm going to be discussing in this video, which is buffers, and then renal mechanisms, which include the kidneys, of course, and respiratory mechanisms, which include the lungs and the respiratory rate. These three things are going to be in charge. Okay, so let's talk about what we're looking at in this picture. So on the left-hand side, we have a beaker into which we are placing hydrochloric acid. On the left-hand beaker, we are placing a substance which is known to be very acidic, which is hydrochloric acid. When we have hydrochloric acid in a solution, it is considered a strong acid. It's a very well-known strong acid, and it dissociates easily and irreversibly. That's what makes it. That is what makes it a strong acid. It dissociates easily and irreversibly. And what I mean by that is that it pulls apart. We have our HCl, of course, together here, and then it immediately dissociates into a hydrogen ion and a chloride ion here. The chloride ion is relatively innocuous. It basically is a chaperone, if you will, for this very caustic hydrogen ion. The hydrogen ion is of particular concern to us, of course. Looking back at this video here, or this picture here, we determined that our acidity is actually based on the concentration of hydrogen ions. So when you have pure hydrogen ions in a substance, this obviously denotes acidity. All right, in addition, these things dissociate irreversibly. They will not go back together. They dissociate completely. They dissociate in a way that they will not go back together into the HCl format. And so if you're writing this equation, which I would recommend, what I would do is I would recommend write HCl arrow, and then hydrogen ions H plus, and the chloride ions Cl minus, just to remind yourself that's how dissociation works. Let's take a look at the right-hand side. This one is a little bit trickier to understand because I think that you're used to things dissociating irreversibly. Like that's kind of how equations work in your mind. So now you need to look at a reversible equation. So we're going to take this weak acid, carbonic acid, H2CO3. We're going to place it in the beaker, and you can see that it does partially dissociate into hydrogen ions. And our friend, the bicarbonate ion, H plus and HCO3 minus. However, you'll notice that some of it actually stays together. So this is what we call partial dissociation. Some of it dissociates, some of it does not. So even in solution, the carbonic acid will still remain a whole piece, like one chunk together and not dissociated. At least part of it will not be. Additionally, this is a reversible condition. In other words, the carbonic acid can dissociate into bicarbonate ion and hydrogen ions, or the hydrogen ions and bicarbonate ions can be placed back together into a carbonic acid substance. So when you're writing this equation, you must write this with a double-sided arrow. Carbonic acid, double-sided arrow, reversible reaction, can dissociate into bicarbonate ion and hydrogen ion. So this is what makes it, this is what makes this stuff um, a buffer. The ability to go back and forth between two different states is very important. And you can see the implications for this immediately. If you have a great deal of hydrogen ions in a substance, and you also have a great deal of bicarbonate ions in a substance, you can basically take your bicarbonate ions and attach it to the hydrogen ions to make this weak acid, carbonic acid. This does not significantly change the pH of the substance which you are studying. And so this allows you to take some of that strong acid out of the substance so that we bring it back to a reasonable pH. So that's the buffer system. That's the bicarbonate buffer system, and this is definitely the most important of them. So if you really want to draw all this out, make sure that you're writing, this equation. This is a very important one. You also must know the names of these substances, and you must know what they are. Carbonic acid is a weak acid. Bicarbonate ion is a weak base. Hydrogen ions represent strong acidity. Okay. So I did want to take you through the other two buffer systems just very quickly. You should be aware of them. So this is the phosphate buffer system. This is the buffer system present in ICF, which is the intracellular fluid, and also in your urine. And the equation goes like this. You have your hydrochloric acid, Na2HPO4. This is monohydrogen phosphate, which is a weak base. Notice that those two things are combined together. Strong acid with a weak base. You start to see the pattern here. Reversible arrow, and it's going to create a weak acid and table salt. So see if you can actually complete this equation without me completing it for you. Take a moment, pause the video. And this is what it looks like. We have sodium chloride, which is table salt, and then this substance, dihydrogen phosphate, NaH2PO4. And so that's the phosphate buffer system. Let's talk quickly about the third buffer system, which is the protein buffer system. This can exist within cells, but it also can exist in your blood supply itself, because remember, you do have proteins in your blood. So anytime you have a large number of proteins, you have a certain amount of ability to buffer pH fluxes just by using those proteins. Okay, so we have our amino acid structure. We have a central carbon with our side chain R, which oftentimes we're very interested in this R group, but in this case, what we're most interested in is actually the two substances attached to the central C. So we have our carboxylic acid group on this side, the carboxyls, the amino group on this side, and those are of importance to us. So this is what we would call an amphoteric molecule. We have a single protein molecule that can function reversibly as an acid or a base. So the exposed carboxyl groups, which we denote COOH, of course there's a double bond in there, C double bond O, single bond OH. These can dissociate to release a hydrogen ion when the pH begins to rise. When you have an alkaline substance and you need to release hydrogen ions in order to buffer into acidity, into a more acid direction, then you can release hydrogen ions from those carboxyl groups. So it looks like this. We have our COOH. Well, irreversibly, just the reversible arrow can become a negatively charged O with an H plus sort of floating off the other side of it. And the exposed bases such as NH2 can accept excess hydrogen ions, and it looks like this. We have our amine group hanging off one side of their amino acid, and we have all these excess hydrogen ions. Well, those hydrogen ions don't need to continue floating around in the substance. They can actually attach themselves directly and reversibly to the amine group to form a partially positive structure that mitigates all of those hydrogen ions floating around and causing acidic problems.